For half a century, human progress has been tied to a single brutal metric: how fast we manipulate binary states inside silicon circuits. Inside a modern hyperscale data center, the ethereal speed of data is replaced by a heavy physical reality. Industrial-scale refrigeration plants operate around the clock, fighting a desperate war against thermal dissipation. These facilities are defined by a physical, aggressive hum. It is the sound of liquid chillers and high-velocity fans working constantly to extract the destructive heat left behind by every calculation. This thermal crisis escalated in the mid-2000s with the collapse of Dennard scaling. As transistor gates shrank to a scale of just a few nanometers, engineers could no longer drop the operating voltage without exposing the switch to quantum tunneling and severe power leakage. This chart maps processor clock frequency against power dissipation density. The exponential red curve of conventional architecture explains why consumer CPU speeds have stagnated around 3 to 5 GHz for nearly 2 decades. Notice where that red curve intersects the dotted line at 80 watts per square centimeter. That is the silicon structural melt boundary. Pushing standard hardware past this threshold forces so much localized power into the microscopic area that the silicon literally warps and melts. To survive this, chip manufacturers entered the era of dark silicon. Significant portions of an integrated circuit must now be intentionally deactivated or throttled during heavy operations, just to keep the physical die intact. Engineers have long treated this immense generation of heat as a mandatory tax levied by the laws of physics. The historical assumption was simple: for a physical medium to think faster, it must burn hotter. Deep exploration into foundational physics reveals that heat generation is a byproduct of structural design. The universe does not actually require information processing to consume energy. The true origin of this thermal bottleneck was pinpointed in 1961 by an IBM theoretical physicist named Rolf Landauer. He sought to establish the absolute mathematical limits of data manipulation. Landauer proved that routing a bit along a wire or changing its logical pathway has no inherent thermodynamic cost. Energy expenditure occurs only when a system is forced to erase or destroy information. This graph charts the exact physical minimum cost of a single bit erasure, as dictated by Landauer's principle. At the 298.15 Kelvin mark, room temperature, the irreducible energy threshold evaluates to about 2.87 zeptajoules per bit. Modern processors erase information billions of times a second because the core block of classical computing, the Boolean AND gate, is fundamentally designed to forget. An AND gate accepts 2 inputs. If the output is 0, the system loses the input's history. 3 electrical configurations collapse into one, permanently wiping away data. This destruction acts as an information dam, converting structured bits into chaotic heat vibrations. While 2.87 zeptajoules seems microscopically trivial, an advanced AI accelerator contains over 100 billion transistors cycling at 3 GHz. Those tiny, irreversible erasures compound into hundreds of watts of concentrated thermal output. Current cooling infrastructure exists to manage the physical consequences of computational amnesia, extracting the heat generated by the constant destruction of data. To construct a machine that never forgets, we must move into the abstract mathematical domain of information conservation and perfectly reversible logic pathways. Reversible computing requires bijective mapping. Every logic gate must have an equal number of input and output lines, ensuring a unique one-to-one correspondence between every possible state. The universal building block for this architecture is the Toffoli gate. It utilizes 3 inputs and 3 outputs to simulate any classical logic gate while maintaining a perfect record of the original state. By knowing the output vector of a Toffoli gate, an operator can run the system in reverse to recover the exact input vector. No data is lost in the process. The Fredkin gate, or controlled swap gate, adds a second layer of conservation. It strictly preserves the total number of ones and zeros passing through it, reorganizing information without creating or destroying it. This functions like an elegant kinetic rail system. Data bits are like cars rolling along tracks. They switch lanes based on control signals, but not a single wheel or chassis is ever discarded. Networks of these gates can assemble complete arithmetic logic units and memory registers, allowing a processor to execute software loops of infinite complexity. Because no bit is ever permanently erased in this bijective system, internal entropy remains constant. The Landauer energy barrier effectively falls to zero. Translating abstract math into physical hardware requires an entirely new way of handling electrical charges. Reversible logic is impossible if standard transistors dump their charge into the system ground wire. Standard circuits rely on an abrupt DC voltage supply. When a gate switches, it crashes charge into the substrate, generating wasted heat with every operation. The solution is adiabatic charging. It replaces the abrupt square wave with a gradual, oscillating AC clock, shown by the smooth sinusoidal curve. Charge is slowly coaxed into transistor channels, avoiding high-velocity collisions that generate heat. When the operation concludes, the circuit path reverses. The residual charge is directed back out of the transistor matrix and stored inside inductors. These inductors act as temporary reservoirs, recycling the stored charge to drive the very next computational cycle. Adiabatic silicon circuits offer a massive 90 to 99% reduction in traditional heat dissipation compared to conventional hardware. Adiabatic implementation functions as a closed-loop electrical recycling plant, capturing and reusing the energy that once escaped as waste. Reaching a state of absolute 0-watt dissipation requires moving beyond silicon. Even with adiabatic charging, standard silicon substrates retain a small amount of inescapable electrical resistance. To eliminate this final trace of friction, we must turn to cryogenic superconducting materials. In this environment, electrical resistance drops to zero, allowing charge to move without generating heat. The foundational hardware component here is the Josephson junction. These microscopic superconducting loops execute reversible operations by channeling individual magnetic flux quanta, operating without any ohmic friction. Engineers still manage a speed-energy trade-off in these systems. Minimum heat requires slow voltage transitions, as pushing the clock speed higher eventually introduces tiny non-adiabatic losses. This friction-free architecture aligns perfectly with quantum mechanics. By definition, the logic driving qubits must be unitary and reversible, making it inherently unburdened by Landauer's erasure penalty. Returning to the power dissipation chart, the green line representing the reversible model remains flat. Even at high frequencies, these architectures bypass the thermal wall that limits silicon. This architecture provides the foundational stability required for the next generation of quantum information systems, far exceeding a mere efficiency upgrade. For decades, we have viewed computation as a noisy, high-pressure industrial task. Reversible computing points toward a future where hardware behaves like a frictionless kinetic sculpture. In this ideal architecture, data bits travel smoothly along coordinated pathways, sliding forward to calculate and backward to verify without emitting a single spark of heat. Computation becomes a perfectly balanced, frictionless kinetic system, folding and unfolding seamlessly without wasting a single joule of energy. As we approach the physical limits of silicon scaling, bypassing Landauer's limit has become an essential roadmap for global computing infrastructure. By building machines that never forget, we liberate technology from the thermal wall, allowing processors to grow infinitely powerful. This realization leads to a future where computation is unbounded by heat, remaining completely cool to the touch, regardless of its power.